Good day, sir. I am Cadet Ricky Griego from BSMT 1-9. I am here to present my navigation project about the three topics about that you gave us. So the first topic that you gave us is the Earth's coordinate system, about the latitude and longitude. The first step is converting the information contained in the real world onto a piece of paper, was to devise a system where everything could be uniquely located in the world. Very early maps, which usually shown small local and regional areas, used a grid technique which relied on simply measuring the distance and direction between points of interest and then plotting these onto the piece of paper. This method assumed that the Earth was flat, with the general agreement that the Earth was, in fact, round. A different methodology needed to be developed. The system that has been developed over many centuries is called latitude and longitude. The location and measurement of latitude and longitude essentially involves complex mathematics, especially geometry, and a series of international agreements or conventions for recording locations on the surface of the Earth. The latitude. The first convention to be developed was latitude. This is based on the long-term astronomical observation about how the sun is perceived to move across the surface of the Earth. This observation also developed the conventions that the sun rises in the east and sets in the west, is, is in the south during a European winter and in the north is European summer. It was agreed that a line around the center of the Earth would be called the equator. This would be numbered as 0 degrees of latitude. From the equator, a series of parallel lines were recognized, with the most northern and southern points being called the North Pole and South Pole. This would be numbered as 90 degrees north and south, respectively 90 degrees north and 90 degrees south. There are four significant lines of latitude were also agreed upon. These are 0 degrees the equator, 23.5 degrees north and south, the tropics called Cancer in the north and Capricorn in the south. Between these two and some time of the year, the sun is directly overhead. Beyond each of these, the sun is never directly overhead. 66.5 degree north and south, the polar circles. 90 degrees north and south, the poles. Beyond the poles and the polar circles, 24 hours of daylight. Midnight sun is possible in summer and 24 hours without any daylight is possible in winter. Because of lines of latitudes are like slices through the earth, they have different lengths. For example, the equator is 40,075 kilometers long. The Antarctic Circle is 17,662 kilometers long. The South Pole is 0 kilometers long. For obvious reason, and longitude. Defining longitude was much more difficult, as could not be based on the observation of movement of the sun. It was in part influenced by the discovery of magnetic north, but ultimately longitude is mostly based on abstract mathematical or geometric concepts. For a considerable period of time, the issue of which line of longitude was to be the primary line could not be agreed. For obvious religious reasons, early European maps often used Jerusalem as the primary line of longitude. Because of its status of a center of learning, other early map makers, such as Ptolemy, had used Alexandria in Egypt. More commonly, though, for patriotic reasons, many countries choose one of their cities. A few European examples are Copenhagen, Paris, and Saint Petersburg in the United States has been chosen. Eventually, in October 1884, at the International Meridian Conference it was agreed that the line of longitude that runs through the Royal Observatory Greenwich in United Kingdom was to be adopted as the standard primary line of longitude. Radiating to the east and to the east would be 180 degrees of longitude. This would meet at the opposite side of the Earth and from a joint 180 degrees line of longitude with 180 degrees east and 180 degrees west being the same line. Lines of longitude are called meridians. Add the two together, combined latitude and longitude together, and we have a system to record the location of any feature on the surface of the Earth uniquely. The second topic is map projection. In cartography, a map projection is a way to flatten a globe surface into a plane in order to make a map. This requires a systematic transformation of the latitudes and longitudes of location from the surface of the globe into location on a plane. Flattering the Earth. It's impossible to flatten the Earth without distorting it in some fashion. Consider an orange peel. If you want to try and play it flat, you have to stretch it, squash it, and tear it. Likewise, with the Earth, we want to make a map. We need to distort the Earth's surface to flatten it. Projection properties. We often talk about map projection in terms of the ways in which they distort or preserve certain things about the Earth, which we call projection properties. There are four properties. Area is the first, and the second is form, and the third is distance, and the fourth is direction. First is area. Maps of this density demand equal area projections. If you're working with data set of person per square mile, for example, your map needs to make sure each square mile looks the same size. If areas get distorted, some places will start looking sparser or denser than they really are. The second is form. Conformal projections are often good for general purpose reference mapping, where we want to keep places looking recognizable and familiar. They are also often used for navigational charts by preserving local angles. They don't distort plots. 45 degrees turn on the Earth looks like a 45 degrees turn on the map. Whereas if angles were distorted, this would not be the case. The third is distance. If you'd like to show visually how far one thing is from another, you're going to need to preserve distance. Sometimes airports use this to show the cities they fly to. The last one is direction. Also helpful for navigation. Sometimes it's useful to show loxodromes as straight lines. The Mercator, for example, was invented for Renaissance sailors to make it easier for them to plot courses. They could draw a straight line on a map, and this would tell them exactly which compass heading to use to head home. On the other hand, if you're piloting an airplane, you might want to show great circles as straight lines so that you can get from A to B while using the least fuel. There are plenty of reasons to preserve each of these properties. The above are simply examples to get you thinking. Some other considerations. How big of an area are you mapping? If you're mapping the world and don't need to preserve a specific property, a compromise projection is your best bet. Does the area of your map tend or run north, south, and east, west? Different projections have different distortion patterns. Some, like the Albers equal area conic, distort more as you go north or south, but don't distort much as you go east or west. So they're good for mapping an area like the United States. They're not so good for mapping a country like Chile, though, which runs north-south. The transverse Mercator, different from plane Mercator, distorts a lot east to west but doesn't distort very much north and south, so it would be a better choice for Chile. What will your readers think about it? For example, while while many readers may be familiar with the Mercator, the less familiar distortions they see on an azimuthal equidistant may throw them off, or perhaps intrigue them and cause them to pay more attention to your map. Likewise, people are used to seeing the US map with something like an Albers equal area conic, which gives it a curved appearance. Seeing the US on a cylindrical equal area might not look right to some readers, despite there are being nothing wrong with either projection. The last topic is general information on a nautical charts for DLAT and DLONG. A nautical chart is graphic representation of a sea area and adjacent coastal regions. Depending on the scale of the chart, it may show depths of water and heights of land, natural features of the seabed, details of the coastline, navigational hazards, locations of natural and human made aids made aids to navigation information and tides and currents, local details of the Earth magnetic field and human-made structures such as harbors, buildings, and bridges. Nautical charts are essential tools for marine navigation. Many countries require vessels, especially commercial ships, to carry them. Nautical charting may take the form of charts printed on a paper or computerized electronic navigational charts. Recent technologies have made available paper charts which are printed on demand, with cartographic data that has been downloaded to the commercial printing company as recently as the night before printing. With each daily download, critical data such as local notices to mariners are added to the on-demand chart files so that these charts are up to date at the time of printing. So they are the sections and abbreviations of nautical charts. It is a section key. A is for chart number or title and marginal notes. B is possessions, distances, directions, and compass. C is natural features. D is cultural features. E is landmarks. F is ports. H is tides and currents. I is depths. J is nature of the seabed. K is rocks, risks and obstructions. L is offshore installations. M is tracks and routes. N is areas and limits. P is lights. Q is buoys and beacons. R is fog signals. S is radar, radio, and satellite navigation system. T is service. U is small craft. And that's all. Thank you for listening, sir.